Assalamualaikum, I'm Neosingyi from S1G2 Group C, presenting our project titled Anemia Prediction using Artificial Neural Network. Our project focuses on developing a feed-forward artificial neural network model to classify anemia status using clinical and hematological features. So, this is a healthcare classification problem using ANN. The main goal is to predict whether a patient is anemic or non-anemic based on 5 blood-related input features. This is useful because early prediction can support faster screening and help users become more aware of their health condition. However, the system is only designed as a decision support tool, and it should not replace the professional medical diagnosis. We're using the anemia dataset from Kaggle, where the original dataset contains 1,421 records, but after data cleaning, we obtained 534 unique records. Removing duplicates is important because repeated data may make the model performance look better than it actually is. The 5 input features used are gender, hemoglobin, MCH, MCHC, and MCV. And the result will be 0, non-anemic, and 1 anemic. For the ANN architecture, we use a feed-forward neural network because our project is a binary classification problem, which means the model only needs to predict 1 or 2 possible outputs. The input layer contains 5 input neurons, representing the 5 selected features. These values are passed forward into the hidden layers, where the model learns the relationship between the blood parameters and the anemia result. The first hidden layer is a dense layer with 16 neurons. This layer helps the ANN learn patterns from the input data. After that, we added a dropout layer with a rate of 0.2. The purpose of dropout is to reduce overfitting by randomly ignoring some neurons during training. This helps the model avoid memorizing the training data too much and improve generalization into the unseen data. Then, the model uses another dense layer with 8 neurons. This second hidden layer further processes the learned patterns before passing the result to the output layer. Finally, the output layer uses 1 neuron with sigmoid activation. Sigmoid is suitable for binary classification because it produces a value between 0 to 1. If the output value is closer to 0, the model predicts the patient as non-anemic. If the output value is closer to 1, the model predicts the patient as anemic. This architecture allows the ANN to perform anemia classification in a structured and efficient way.
In this slide, I will explain the training setup used for our artificial neural network model. Before training the model, the dataset was divided into 3 parts. We used 70% for training, 50% for validation, and 15% for testing. The training set was used to teach the neural network and update its weights. The validation set was used to monitor the model performance during training, while the testing set was reserved for the final validation. After splitting the dataset, we apply feature normalization using standard scalar. This step standardizes the input value so that all features are on a similar scale. Normalization helps the neural network learn more efficiently and improve training stability. For optimization, we use the ADAM optimizer. ADAM is widely used because it automatically adjusts the learning rate and helps the model converge faster and more effectively. The loss function selected was binary cross entropy, which is suitable because our project is a binary classification problem with 2 possible outputs, anemic and non-anemic. To prevent overfitting, we implemented early stopping. During training, the model continuously monitors the validation loss. If the validation loss does not improve for 10 consecutive epochs, the training process stops automatically and restores the best performance model weight. Finally, the neural network learns through backpropagation, where prediction errors are propagated backward through the network to update the weights and reduce feature error. Overall, this training setup helps the model learn efficiently while maintaining good generalization performance on unseen data. After setting up the dataset, optimizer, loss function, and training process, we can now examine how the model performed during training through the accuracy and loss graph shown in the next slide. Next, I will explain the training accuracy result of our artificial neural network model. These graphs show the training accuracy and validation accuracy across 100 training epochs. At the beginning of the training process, the accuracy is relatively low, around 45%. This is because the neural network has not yet learned the relationship between the input features and the target output. As training continues, we can observe that both accuracy curves increase rapidly during the first 20 epochs. This indicates that the model is successfully learning important patterns from the dataset. The input features used in this project are gentle, hemoglobin, MCH, MCHC, and MCB. During training, the NN continuously adjusts its weights through backpropagation to improve its predictions. After approximately 30 to 40 epochs, the improvement becomes more gradual and the accuracy starts to stabilize. Near the end of training, both the training accuracy and validation accuracy reach around 98%. One important observation is that the two curves remain very close to each other throughout the training process. The validation accuracy follows the training accuracy closely without showing a significant gap. This is a positive sign because it indicates that the model is not simply memorizing the training data. Instead, it is able to generalize well when evaluated on unseen validation data. Therefore, the accuracy graph demonstrates that our NNN model learns effectively and achieves a very high level of classification performance.
Thank you, Kylie. Okay, right now I will tell about the slide 7 training loss. This slide shows how our model prediction error decreases as it learns. You can see both the training and validation loss follow a smooth downward trend. That means the model is consistently reducing error without sign of overfitting. In simple terms, lower loss means the model is becoming more confident in its prediction. By the end of training, both curves stabilize near zero, showing that our neural network learn effectively. Now for our slide 8, final model performance. Here we present the final evaluation result on the testing set. Our model achieved 97.53% accuracy, a test loss of 0.067, and a ROC AUC score of 0.9975. These numbers indicate excellent performance. The model can clearly separate anemic and non-anemic cases. The high AUC value, close to 1.0, means the classifier maintains a strong true positive rate with very few false positives. Overall, this confirms that our neural network is reliable for anemia prediction and can serve as a decision support tool in healthcare.
Next, I will explain the ROC curve analysis of our model. The ROC, or Receiver Operating Characteristic Curve, is used to evaluate how well a classification model can distinguish between different classes. In our case, the classes are anemic and non-anemic patients. As shown in the graph, the ROC curve stays very close to the top left corner. This indicates that the model achieves a high true positive rate while maintaining a low false positive rate across different classification thresholds. The area under the curve, or AUC, is 0.9975. Since an AUC value ranges from 0 to 1, a value this close to 1 indicates excellent classification performance. This means our artificial neural network can accurately separate anemic patients from non-anemic patients with very few classification errors. For anemia prediction, this is especially important because missing an actual anemia case, which is known as a false negative, could delay further medical examination and treatment. Therefore, a high AUC score gives us confidence that the model is effective for screening purposes. Moving on to the findings and limitations of our project. One of the key findings is that hemoglobin showed the strongest relationship with anemia status. This is expected because hemoglobin level is one of the main medical indicators used to diagnose anemia. We also found that removing duplicate records during data pre-processing improved the quality and fairness of the dataset. This helped the model learn more reliable patterns from the data. Overall, the performance metrics including accuracy, loss, ROC, and AUC indicate that the artificial neural network successfully learned meaningful patterns and achieved strong prediction performance. However, there are several limitations. After cleaning the dataset, Only 534 unique records remain. This relatively small dataset may not represent the full diversity of real-world patients. In addition, the dataset was obtained from a public source and may not reflect all clinical conditions or demographic groups. Therefore, before applying this model in real healthcare settings, it should be validated using larger and more diverse clinical datasets. Despite these limitations, the results demonstrate the potential of artificial neural networks as a decision support tool for anemia prediction.
To wrap up our presentation, our project successfully designed and implemented a feed-forward artificial neural network tailored for the critical task of predicting anemia. By leveraging just 5 routine hematological and clinical features, which is gender, hemoglobin, MCH, MCHC, and MCV, we have demonstrated that a streamlined machine learning architecture can extract highly meaningful diagnostic patterns. The empirical results speak for themselves. Our network achieved an exceptional test accuracy of 97.53% and a near-perfect ROC-AUC score of 0.9975, proving the model maintains an excellent true positive rate while keeping false positive at a minimum. Why does it matter in a practical healthcare setting? In clinical workflows, optimizing for a high recall rate is vital because a false negative could dangerously delay essential medical interventions, while our findings show that hemoglobin holds the strongest predictive relationship with anemia status. This model acts as a powerful, rapid screening tool to assist clinicians in faster decision-making before extensive laboratory confirmations are finalized. However, we must emphasize that this system is designed strictly for decision support, not as a placement for expert professional diagnosis. Before we finish, we would like to address a critical technical point regarding our data. Why did we remove so many records? We cleaned the dataset from 1,421 down to 534 unique entries specifically to prevent data leakage. If we had kept duplicates, the model might have simply memorized specific expressions, giving us a fake accuracy. By using only unique records, we ensure our 97% accuracy is authentic and reflects true learning on unseen data. Furthermore, to ensure this reliability, our architecture used a 0.2 dropout layer, which forced the network to learn generalized patterns rather than memorizing the data, actively preventing overfitting. This is our training and validation curves follow each other so closely. These results showcase the immense potential of AI-driven tools in modern healthcare. On behalf of Group C, thank you so much for your time and attention.